For a very long time, humanity has misunderstood the very galaxies we live inside and gaze upon each night. We once believed they were simple, stable, and easily grasped structures, yet layer after layer of cosmic dust and the limits of light itself quietly concealed the truth. What, then, caused our maps of the universe to remain nothing more than faint sketches for centuries, and what is now slowly emerging behind those invisible veils? Today's journey invites you into a deeper stillness, where old misconceptions are gently illuminated by new observations. If you feel a sense of curiosity stirring, leave a comment, tap like, share this journey, and subscribe to the channel to walk with us over time, and to join our community of faith and contemplation. Now, let your breathing soften, and prepare to begin tonight's cosmic voyage. When we look up at the night sky, it is natural to imagine that our own galaxy should be the place we understand best, the familiar structure that everything else can be compared to. Yet, for a long time, even the most basic questions about the Milky Way have stayed uncertain. How many stars it truly holds, how many spiral arms it carries, how its disk and central bulge are arranged in space. All of these have lived in a wide range of estimates and sketches, more like guesses than a precise map. Our story begins with this quiet puzzle that the vast system we live inside remains strangely hard to picture. We can picture ourselves as people standing in a large house with no windows, trying to understand the building only from the corridors we happen to walk through. From far away, another house might be easy to see in outline, its roof and walls clear against the surroundings. From inside our own, the view is blocked by doors and dividing walls, by beams and rooms stacked in front of each other. In a similar way, we live inside the thin disk of the Milky Way, surrounded in every direction by clouds of gas and dust, and by stars overlapping along our line of sight. When we look outward with ordinary telescopes that use visible light, much of the galactic plane forms a crowded band where distant regions simply sink out of view. Astronomers even have a name for the most obscured part of this band, around the center of the galaxy. They call it a zone of avoidance, not because anyone chooses to avoid it, but because dust in that direction absorbs and scatters so much starlight that the deeper structure becomes hidden. It behaves a little like an interior wall in our imagined house, a barrier that keeps us from seeing what the next rooms look like. Behind that dusty wall lies the crowded bulge of the galaxy and the densest star fields. Yet, from our vantage point, they blur into a bright, mottled glow. Because of this, even simple numbers have stayed surprisingly flexible. Rough counts of stars in the Milky Way land somewhere between about 100 and 400 billion. A range so wide that it feels more like a hazy outline than a firm measurement. The number of spiral arms has been debated for decades, with some studies favoring 2 main arms, others drawing 4 more elaborate patterns, and some suggesting that the arms themselves may be patchy and uneven rather than clean. Textbook spirals. The difficulty does not come from a lack of skill or care, but from the awkward fact that we are trying to map a structure from deep inside it, looking through the very material we wish to chart. For a moment, we can let this thought drift. The idea that our cosmic home has long been more assumption than map. One of the core reasons our picture has remained uncertain lies in the way distances work in astronomy. To perform more than a flat sketch of the sky, we need a way to place each star not just on a dome above us, but at the right distance in 3 dimensions. Yet most stars do not conveniently tell us how far away they are. Only a small fraction belong to special families like Cepheid variables or RR Lyrae stars, whose rhythmic changes in brightness follow patterns that reveal their true power. For the countless ordinary stars, we face a basic ambiguity. A dim point could be a small star nearby or a large star far away, and a bright point might be close or simply very luminous. In everyday life, our brains solve similar puzzles automatically by using the slight difference between our 2 eyes. If we hold a finger in front of our face and take turns covering each eye, the finger appears to shift against the background. The closer it is, the more it shifts. This tiny apparent motion is called parallax. Our eyes are only a few centimeters apart, so the effect is noticeable only at short distances. but the principle itself works at any scale. Astronomers long ago realized that if Earth's orbit around the Sun could serve as a wider version of that baseline, then stars should show tiny shifts on the sky as Earth moves from one side of its orbit to the other during the year. These shifts are extraordinarily small, far beyond what our eyes can see unaided. Measuring them from the ground through a moving, shimmering atmosphere adds further difficulty. Even so, early attempts at parallax measurements allowed distances to the nearest stars to be estimated. Over time, better instruments improved the reach, but the method remained challenging. For most of the Milky Way, especially toward the crowded central regions and along the dusty plain, accurate distance measurements were scarce, and our three-dimensional map stayed patchy. We could draw an artist's view of a spiral galaxy and say, our Milky Way might look something like this, but we could not yet fill in the fine structure with confidence. This is where the Gaia mission enters the story, not as a single photograph, but as a dedicated observer designed to measure parallax and motion with exceptional precision for an enormous number of stars. Launched by the European Space Agency, Gaia orbits around a point in space called L2, a location on the night side of Earth where the gravity of our planet and the Sun combine in a way that allows a spacecraft to maintain a relatively stable position. From there, away from most of the glare and interference, Gaia slowly spins and scans the sky, tracing out patterns that eventually cover almost every direction. The spacecraft carries two telescopes that point at different parts of the sky, but both feed light into the same large focal plane, a kind of mosaic camera with close to 1 billion individual detecting elements. Over more than a decade, Gaia has repeatedly swept over the same stars again and again. Each pass adds more data about where a star appears on the sky, how its position shifts with Earth's orbit, and how it drifts over time due to its own motion through the galaxy. In total, the mission has collected on the order of trillions of individual measurements, distilled into precise information for around 2 billion stars. For each of these stars, Gaia tries to measure not just where it is, but how far away it lies, how it is moving, how bright it appears, what its color suggests about its temperature, and even hints about its chemical composition. In effect, every point of light becomes not only a coordinate in three-dimensional space, but also a small record of its physical state. When we place all of these records together, we begin to see the Milky Way not as a flat band, but as a thickened disk with spiral structure. A central bulge, star clusters in its halo, and streams of stars that trace past encounters. It is striking to remember that even 2 billion stars are only a fraction of the galaxy's full population, a sample drawn from a much larger whole. Yet, the way this sample is distributed across the disk and bulge makes it especially powerful. Instead of a handful of isolated landmarks, we now have a dense web of positions and motions that allow astronomers to trace patterns in the galactic disk, to identify overdensities and gaps, and to follow subtle ripples that hint at past disturbances. The Milky Way begins to appear not only as a shape, but as a system in motion, woven together by gravity. A quiet pivot happens here, from space to time. Once positions and velocities are known with enough precision, the galaxy is no longer just a static structure. The data can be used to reconstruct how stars have moved, and how they will move, over long stretches of cosmic time. Instead of a single frame, we obtain the ingredients for a long, continuous sequence. We can imagine those 2 billion Gaia stars as points in a vast, dark volume, each one carrying a little arrow that shows its direction of travel. With models of the Milky Way's gravitational field, astronomers can follow those arrows backwards, rewinding the motions to see how certain groups of stars may once have been more compact, perhaps belonging to a smaller galaxy that merged with ours. They can follow them forwards, too, letting orbits trace long paths around the galactic center, watching how the disk slowly shifts its patterns over millions of years. The familiar spiral arms, in this view, become regions where stars and gas spend more time, guided by waves of higher density that circle the galaxy. This way of seeing reconnects with the earlier uncertainty. For a long time, we held static pictures of galaxies, sketched from photographic plates and brightness profiles. With Gaia's long-term survey, the Milky Way itself becomes a moving, evolving object. Some stars form streams that loop through the outer halo, remnants of dwarf galaxies that were gradually drawn in and stretched out. Others outline the bar-like structure in the central regions, where orbits bend into elongated shapes under the combined pull of the disk and bulge. The once simple question, how many arms does the Milky Way have, gives way to a more subtle understanding of patterns that can change over time. In the background of this story, other instruments add their own layers. Infrared surveys from telescopes such as Vista in Chile can look through much of the dust that hides the inner galaxy in visible light, revealing countless young stars and clusters in the bulge and along the plane. Where Gaia's strength lies in motion and precise distances, these infrared maps bring out populations that were nearly invisible before, especially in the crowded central regions. Together, they begin to outline both the ancient, densely packed heart of the Milky Way and the regions where new stars are still forming. The combination of these views, visible and infrared, static brightness, and measured motion, builds toward a new kind of map. It is a map that does not only show where things are, but also hints at where they came from and where they are going. Our galaxy's past mergers and its slow changes in shape, its streams and clusters and spiral patterns all start to appear as parts of one long, continuous process. We can let that process remain unfinished in our minds. The Milky Way does not need to be solved or fixed in a single picture. It can stay as an unfolding structure, a home whose rooms are still being traced by quiet instruments far from Earth, as they watch stars shift, one by one, against the dark. Gaia has begun to show us that our galaxy carries a long record of encounters and motions that once stayed hidden in the background. From small groups of stars that move against the main flow to the broad pattern of the spiral arms and the invisible mass that guides them. What seemed, for a long time, like a single hazy shape in the sky turns into a layered story of origin, growth, and slow rearrangement. When the first large Gaia catalog arrived, it held precise positions and motions for millions of stars in the Milky Way. Inside that sea of data, researchers noticed something unexpected. Among roughly 7 million stars examined in detail, about 30,000 moved around the galactic center in the opposite direction from most of their neighbors. On a map of orbital motion, almost every point followed the usual rotation of the disk. Yet a small fraction traced paths that looped the other way, like a narrow stream flowing against a broad current. We can picture a wide ring road seen from above, filled with cars orbiting a city in one shared direction. If we mark each vehicle as a small dot moving along its lane, the overall pattern is smooth. Now we imagine a thin streak of dots moving the other way, tracing out a long, coherent ribbon. In the galaxy, that ribbon corresponds to stars whose colors and brightness do not match the typical population of the Milky Way's disk. Their chemical fingerprints suggest they were born somewhere else, in a smaller system with a different history, before being folded into our own. By combining Gaia's motions with models of how galaxies interact, astronomers traced this retrograde group back to the remnants of a dwarf galaxy that merged with the Milky Way long ago. This ancient companion, often called Gaia Enceladus, seems to have approached, been drawn in by our galaxy's gravity, and slowly dispersed. Its stars now span a wide region of the halo, some moving in orbits tilted to the disk, others looping in elongated paths that still carry the memory of their original trajectory. In this way, Gaia's three-dimensional map of about 2 billion stars over a decade of observations does more than show where stars are today. It hints at the Milky Way's eating habits, the quiet accumulation of smaller galaxies over cosmic time. The retrograde stream is only one example. As more of Gaia's data have been explored, additional groups of stars have appeared with shared motions and shared chemistry, each pointing to a separate infall event. Current studies suggest that the Milky Way may have absorbed on the order of half a dozen dwarf galaxies, each leaving behind elongated streams, clumps, and patterns in the halo. One of the most prominent companions, the Sagittarius dwarf galaxy, has likely passed through the Milky Way's disk several times over the last few billion years. With every passage, some of its stars are left behind, stretching into long arcs that wrap around the galaxy. From a distance, we could imagine the Milky Way's halo as a wide, faint glow with subtle streaks running through it, like threads of a different shade woven into a much larger fabric. These stellar streams curve above and below the disk, sometimes intersecting our own position, and Gaia's precise measurements allow astronomers to follow their paths and reconstruct their origins. The globular clusters that crowd the regions near the galactic center also carry information. Some appear to have been born in our galaxy, while others likely arrived as part of these smaller systems, adding their dense, old star groups to the growing collection around the galactic bulge. In this view, the Milky Way does not grow in isolation. It is built from many smaller units, assembled over billions of years. The standard cosmological picture, in which large structures form from the gradual merging of smaller ones, finds a very direct expression here. Each stream and cluster becomes a kind of archival trace, and Gaia's combination of position, motion, and chemistry is the tool that allows those traces to be read. We start to see the galaxy as a layered record of past encounters and long, drawn-out interactions. While the halo preserves these stories of past mergers, the disk itself poses another question. Spiral arms are among the most striking features of galaxies like ours, sweeping outwards in broad curves. If we imagine the Milky Way as a solid disk that simply rotates, the inner regions would complete their turns more quickly than the outer regions. Over long time scales, any initial pattern would wind tighter and tighter, twisting the spiral arms into narrow coils. Yet when we look at other spiral galaxies, and when we reconstruct the pattern in our own, the arms appear as open, persistent features rather than tightly wound threads. One way to understand this is to think of the arms not as fixed collections of stars, but as regions where stars and gas crowd together temporarily. A familiar comparison is traffic on a busy highway. The cars move forward, but sometimes a denser region forms where vehicles slow slightly, bunching up. As time passes, individual cars enter and leave this cluster, yet from high above, the denser patch appears to drift along the road as a recognizable feature. In the density wave picture of spiral structure, the arms are similar. They are patterns in the gravitational field where matter moves more slowly through a region of higher density, triggering star formation as gas clouds are compressed. Newborn stars in these regions are often bright and short-lived, so they highlight the arms, giving them a luminous edge. Older stars, with longer lifetimes, drift away and fill the rest of the disk more evenly. Gaia's measurement of proper motions, small shifts in position on the sky over time, helps to map how stars move through and around these patterns. The spiral arms, in this sense, are not solid objects but moving crests in a wide, rotating disk, shaped both by the galaxy's mass distribution and by past interactions with smaller companions that can disturb the disk and seed new patterns. A deeper layer of the Milky Way's motion emerges when we look at how fast stars orbit at different distances from the center. Classical mechanics offers a simple expectation. If most of the mass were concentrated in the luminous part of the disk and bulge, stars farther out should circle more slowly, in a way that falls off with distance, somewhat like planets in a planetary system. Observations of our galaxy and many others show something different. Beyond a certain radius, the orbital speeds do not decline as expected. They stay almost constant over a wide range of distances, forming what astronomers call a flat rotation curve. We can imagine a spinning disk sprinkled with grains of sand. If we only counted the visible grains and calculated how fast those at the edge should move to stay in orbit, we would predict a certain speed. Instead, we find that the outer grains move faster than that calculation would allow, as if there were an additional, unseen mass extending beyond the visible disk and bulge. To reconcile this, astronomers infer the presence of a vast halo of dark matter surrounding and penetrating the galaxy, a form of matter that interacts through gravity but does not emit or absorb light in any straightforward way. Gaia's data contribute here as well. By mapping the motions of stars in the disk and halo, and by combining those motions with measurements of gas clouds and with observations of distant galaxies whose light is bent by gravitational lensing, researchers can refine models of how much dark matter is needed, and how it is distributed. When we observe clusters of galaxies acting as lenses, bending light from even more distant systems, we see a similar pattern of extra mass. These independent lines of evidence together support the idea that galaxies, including our own, are embedded in extended halos of unseen material that shape their rotation and their long-term evolution. While Gaia tracks motions and distances in visible light, instruments like the VISTA telescope in Chile add an important complementary view. VISTA surveys the sky in infrared wavelengths that can pass through much of the dust in the Milky Way's plane. Over years of observations, it has built the largest and most detailed infrared map of our galaxy, uncovering over 1 billion previously hidden objects and revealing rich populations of young stars in the bulge and along the inner disk. Where visible light maps might show a dark lane, infrared images often reveal dense star fields and clusters that were simply obscured. By combining Gaia's precise three-dimensional map with VISTA's deep infrared view, astronomers can trace both the ancient heart of the galaxy, the old bulge, and its surrounding globular clusters, and the regions where new stars continue to form, especially along the spiral arms and in the inner disk. The same techniques extend outward, allowing us to see galaxies at different stages. Sharply defined spirals with active star formation, smoother lenticular systems where star birth has slowed, and large elliptical galaxies whose shapes and motions reflect many past mergers. Our own Milky Way sits somewhere along this spectrum, its history written in streams, arms, and a halo of dark matter. The more completely these maps are drawn, the more the Milky Way appears as a living structure in motion rather than a fixed picture. Streams continue to be discovered, subtle ripples in the disk are gradually charted, and the distribution of dark matter is refined with each new survey. The overall pattern remains: a persistent rotation, a set of broad spiral arms, a crowded central bulge, and a surrounding cloud of unseen mass, all moving together through space. We can let that pattern continue in our thoughts without needing a final conclusion. As the galaxy turns and its stars follow their paths, step by unhurried step, across intervals of time far longer than any single story can contain. While Gaia follows the positions and motions of stars in visible light, another telescope watches the Milky Way in a different way, tuned to wavelengths that slip past the dust that hides our galaxy's crowded heart. From a mountaintop in Chile, under dry air and wide skies, VISTA turns its wide infrared camera toward the band of the Milky Way and patiently assembles a map that feels less like a surface picture and more like a view into layers that were once concealed. The dust between the stars is made of tiny grains, often comparable in size to the wavelengths of visible light. When starlight in those shorter wavelengths passes through a cloud of dust, it is scattered and absorbed, dimmed and reddened until distant regions fade from view. In optical images of regions such as the Lobster Nebula or the Trifid Nebula, dark lanes and cloudy silhouettes carve across the star field, cutting us off from whatever lies behind them. Infrared light, with its slightly longer wavelengths, interacts differently with these grains. It passes through more easily, not completely unaffected, but far less impeded. So that where visible light shows a dark patch, infrared images reveal a crowded background of stars that were always there, simply hidden from ordinary sight. VISTA, a 4-meter class telescope operated by the European Southern Observatory, was designed specifically for this kind of work. Its wide-field infrared camera, VIRCam, observes at wavelengths just beyond the red end of the spectrum, out to about a micron and beyond. Over more than a decade of surveys focused on the bulge and plane of the Milky Way, often referred to as VVV, and its extension VVVX, VISTA has taken hundreds of thousands of images. When these images are combined, they form the largest and most detailed infrared map of our galaxy so far, containing well over 1 billion individual sources and occupying hundreds of terabytes of data. Each point in that map is a star, a cluster, or a distant galaxy that can now be studied in a way that was not possible before. The effect of this change in wavelength is easy to picture if we imagine 2 photographs of the same nebula. In the first, Taken in visible light, a cloud like the Trifid Nebula appears as a bright, structured object with opaque dust lanes that cut across a glowing background, almost like ink strokes across a lantern. In the second, taken in infrared, many of those dark lanes soften, and behind them a curtain of faint stars emerges, adding depth and structure. Vista's surveys apply this approach not to a single field, but to a vast swath of the Milky Way's inner regions, including parts of the so-called zone of avoidance, where visible light surveys struggle the most. From this new view, unexpected signposts begin to appear. When astronomers examined Vista's images of the Trifid Nebula and its surroundings, they did not only see the gas and dust of the nebula itself. Behind that foreground structure, deeper along the line of sight, on the far side of the galaxy's center, they identified two Cepheid variable stars that had not been recognized before. These stars are young, massive, and rhythmically unstable. Their brightness rises and falls in a regular pattern, and the length of that cycle is tightly linked to their true power. By measuring how quickly they pulse, astronomers can infer how luminous they really are, and by comparing that with how bright they appear, they can estimate their distance. In visible light, the dust along the line of sight to these Cepheids makes them hard to use as precise markers. In the infrared, where extinction is reduced, their measured brightness is closer to what it should be, and the distance estimate becomes much more reliable. The two Cepheids behind the Trifid Nebula are particularly valuable because they sit in a region that was difficult to probe, deep beyond the galactic center. They extend the reach of the so-called distance ladder, the chain of overlapping methods that allow us to step outward from the solar system to the Milky Way, and from the Milky Way to nearby galaxies and clusters. Step by step, Cepheids observed in infrared help calibrate other distance indicators, linking the inner structure of our galaxy to scales that eventually reach out toward distant galaxy clusters and the lenses they form. Closer to the heart of the Milky Way, Vista's view reveals a different kind of pattern. Before these infrared surveys, the central bulge was often pictured as a realm dominated by old reddish stars, a crowded stellar city whose inhabitants formed long ago. When researchers used Vista data to search for variable stars in this region, they found hundreds of Cepheids, and among them a smaller subset stood out. A few dozen so-called classical Cepheids, with ages of less than about 100 million years. These are not old residents. They are young, short-lived stars that have formed relatively recently on galactic timescales. When the positions of these young Cepheids are plotted in 3 dimensions, they do not form a random cloud. Instead, they outline a thin structure aligned with the plane of the Milky Way, a narrow disk of young stars that passes straight through the bulge. It is as if, within the old central region, a bright, newly built roadway of young stars extends across the city, tracing where gas has been funneled inward and compressed into new stellar generations. This pattern suggests that star formation in the inner galaxy has not simply shut down. Gas continues to reach the central regions, perhaps guided by the barred structure we infer from other observations, and there it settles into a thin layer that still produces bright, massive stars. Alongside these youthful markers, Vista's surveys of the bulge have uncovered a contrasting group of variables. RR Lyrae, stars very close to the galactic center. RR Lyrae are small, old stars, with ages of 10 billion years or more. They belong to an ancient population that typically resides in the halo and in globular clusters. Finding a group of them near the very center of the Milky Way hints at a different layer of history. One way to picture it is to imagine a bustling modern square that still contains a small cluster of very old buildings, reminders of a much earlier settlement around which the current city has grown. In galactic terms, those RR Lyrae may trace the remnant of a primordial globular cluster that wandered too close to the central regions. Over time, the strong gravitational field near the core of the Milky Way can pull such a cluster apart, scattering its stars into the surrounding bulge. The cluster ceases to exist as a bound object, but its characteristic stellar population remains. The presence of these stars supports scenarios in which part of the bulge formed not just from inflowing gas, but also from the contributions of many ancient clusters that sank inward and dissolved, adding their stars to the central mix. Further out from the exact center, Vista's infrared maps extend into the halo and the outer disk, where they reveal both compact and loose groupings of stars. Dense, spherical, globular clusters are like tight knots in the wider field, while open clusters are looser gatherings of young stars, often associated with recent star formation in the disk. The infrared surveys have led to the discovery of new globular clusters that had been overlooked, their light previously hidden by dust. They also reveal nearly 100 new open clusters, including some on the far side of the Milky Way, beyond the bulge, where extinction is strong in visible light. These clusters serve as traces of structure. Globular clusters often act as durable fossils of past events. Some appear to have formed within the Milky Way, while others likely arrived with dwarf galaxies that were later absorbed. Their orbits and chemistry, combined with Gaia's precise measurements of motion, help reconstruct which clusters might share a common origin. Open clusters, by contrast, indicate where the disk has formed stars more recently. Their distribution along the spiral arms and near the plane shows where gas clouds have collapsed in the recent past, complementing Gaia's picture of moving streams and star-forming regions. Together, these pieces assemble into a three-dimensional map of remarkable depth. Gaia provides accurate distances and motions for around 2 billion stars across the sky, revealing past mergers, streams, and the overall rotation of the Milky Way. Vista's long-term infrared survey adds the largest and most detailed map of the inner galaxy in wavelengths that penetrate dust, uncovering over 1 billion previously hidden objects and entire populations of young stars in the bulge. When these datasets are combined, astronomers can trace both the ancient core of the galaxy, its old clusters, halo stars, and dissolved remnants of early structures and its ongoing star formation, visible in young clusters and Cepheids embedded in the disk and central regions. The result is not a single static chart, but a shifting, layered picture in which different stellar populations mark different times and processes. Old RR Lyrae near the center recall the earliest construction of the bulge. Young Cepheids in a thin inner disk hint at continued gas inflow and star birth. Globular clusters in the halo trace past accretion events, and open clusters follow the present-day pattern of star formation across the disk. The infrared view dissolves some of the walls that once obscured these connections, turning the inner Milky Way from a flat band of light into a structure with depth and history. Beyond our own galaxy, similar techniques are applied to other systems, where visible and infrared observations combine with the bending of light by massive galaxy clusters acting as lenses, allowing us to see fainter and more distant objects. Our home galaxy becomes one case among many, a nearby laboratory whose details we can study most thoroughly. Yet even here, the work of mapping continues, as surveys like Gaia and Vista keep adding stars, clusters, and distant background sources to their catalogues. The hidden patterns of the Milky Way slowly emerge, one wavelength at a time, as the galaxy turns and its stars remain quietly in motion. Some of the brightest objects in the sky were first noticed in a way that did not involve light at all. In the middle of the 20th century, as radio astronomy expanded, surveys of the sky began to reveal compact sources that shone strongly at radio wavelengths. When astronomers tried to match those radio positions with ordinary photographs, they often saw nothing unusual. The locations corresponded either to blank regions or to points of light that looked like ordinary stars. The radio maps said that something very energetic was there. The optical images offered almost no clue. It was as if we were listening to a landscape with a radio receiver and hearing powerful transmitters scattered across the horizon. Yet, when we stepped outside and looked in those directions, all we saw were a few faint points. As larger optical telescopes were brought into the effort, some of these radio sources were matched to star-like objects whose light could be broken into spectra. Those spectra turned out to be strange. The familiar patterns of absorption lines were shifted far toward the red, indicating that these sources lay at enormous distances, in galaxies far beyond our own. If the shift was interpreted as the effect of cosmic expansion, then the apparent brightness of these objects implied a true power output far greater than that of a normal galaxy. They looked star-like on the sky, but their luminosity belonged to something much larger. To reflect this, they were called quasi-stellar radio sources, or quasars, a name that kept the sense of their star-like appearance while hinting that their nature was something quite different. Over time, it became clear that many quasars were not just strong radio emitters. Some were radio quiet, but very bright, at optical and other wavelengths. Deep imaging revealed that they sat at the centers of faint host galaxies, sometimes surrounded by distorted structures and, in some cases, by distant galaxy clusters that acted as gravitational lenses, splitting and magnifying their light. The working picture that emerged was that a quasar is the bright, compact core of a galaxy whose central engine is particularly active, powered by matter falling toward a massive object in the middle. The central object is thought to be a black hole, with a mass millions or even billions of times that of the Sun, embedded in the Milky Way, like disks and bulges of distant galaxies. Around this black hole, gas and dust spiral inward, forming an accretion disk where friction and compression heat the material to high temperatures. As matter loses energy and drifts inward, the gravitational energy it sheds is converted into radiation across a wide range of wavelengths: ultraviolet, optical, X-ray, and sometimes gamma-ray. In many systems, strong magnetic fields thread the disk and the region close to the black hole, guiding some of the inflowing material into narrow jets that stream outward along the rotation axis. In this way, a region smaller than our solar system can outshine an entire galaxy of stars. The disk glows with intense continuum emission. The surrounding gas clouds produce broad spectral lines, and the jets carry energy outward, sometimes for tens or hundreds of thousands of light years, interacting with the gas between galaxies. We observe these processes through the combined efforts of ground-based telescopes and space observatories that record X-rays and higher-energy photons, each adding a different layer to the picture. Quasars also serve as markers. Because they can be seen across large fractions of the observable universe, they provide reference points for mapping cosmic expansion, and their light, passing through intervening clouds and clusters, carries signatures of the matter in its path. When a distant quasar is aligned behind a massive galaxy cluster, the cluster's gravity bends and magnifies the light, creating arcs or multiple images. These gravitational lenses help reveal the distribution of mass, including dark matter, in the clusters themselves. In this way, quasars become both beacons and probes, telling us about the environments around them and about everything between. Yet the scales involved in a distant quasar can make the details elusive. The central region is too compact and too far away for us to resolve directly. To study the physics of accretion disks and jets more closely, astronomers look for systems that use the same processes but on smaller scales, where distances are measured in thousands rather than billions of light years. Within our own Milky Way, such systems exist in the form of X-ray binaries that host black holes or neutron stars. When the compact object in a binary is a black hole of a few tens of solar masses, and when its companion star feeds material into an accretion disk, the system can produce a scaled-down version of the quasar phenomenon. Gas from the companion star flows through the inner Lagrange point, or via a stellar wind, forms a disk around the black hole, heats up, and emits X-rays. Under the right conditions, collimated jets form and carry energy outward at significant fractions of the speed of light. Because these systems mirror many of the physical ingredients of quasars, but are located in our own galaxy, they are often referred to as microquasars. The power they emit is far smaller than that of a true quasar, and they pose no global hazard. Yet they reproduce the same basic configuration: compact object, accretion disk, outflowing jets, and a surrounding medium that responds to the energy being channeled through it. One of the first and most studied examples of such a system is known as SS-433. It sits within the Milky Way, embedded in an extended nebula, and for decades it has served as a nearby laboratory where the structure and behavior of jets can be observed in far more detail than is possible for distant quasars. From the bright cores of galaxies at cosmological distances, our attention drifts inward to this compact system within our own disk, where similar processes unfold on humanly accessible scales and times, allowing us to watch the way energy leaves the vicinity of a black hole and shapes the space around it. In the region of sky where SS-433 lies, we are no longer looking at a remote galactic nucleus thousands of megaparsecs away, but at a binary system within our own Milky Way. One of the members is a large, luminous star, a kind of supergiant whose outer layers can be drawn outward under the influence of its companion's gravity. The companion is thought to be a stellar mass black hole, the collapsed remnant of a once massive star. Together, they orbit a common center of mass, with gas streaming from the extended star toward the compact object. As this gas spirals inward, it does not fall straight in. Conservation of angular momentum forces it into a flattened disk around the black hole, where friction and magnetic turbulence heat it to X-ray temperatures. The inner regions of the disk glow intensely, and some of the inflowing matter is redirected along the system's rotation axis into two narrow outflows, one on each side of the disk. These outflows are the jets of SS-433, extending away from the binary in opposite directions, roughly perpendicular to the orbital plane. They can be imagined as twin streams emerging from a rotating nozzle, plunging through the surrounding nebula. Measurements of spectral lines from matter in the jets show that they move at a substantial fraction of the speed of light. Unlike purely radiative beams, they carry actual particles, electrons, ions, and magnetic fields flowing outward through the interstellar medium. As they propagate, they carve channels in the gas and inflate larger structures, leaving behind traces in radio and X-ray images that mark their paths. Close to the source, near the binary itself, the jets remain narrow and relatively well collimated. This inner region spans a distance of only a few light-years and traces the immediate environment of the accretion disk. Beyond that, the flow encounters denser gas and begins to interact more strongly with its surroundings. At larger distances, the jet material slows, spreads, and forms broader, more diffuse regions of emission. In SS-433, observations distinguish between these inner jets, closely tied to the binary, and outer jets that extend much farther, reaching tens or hundreds of light-years from the source. The outer jets are where some of the highest energy photons are detected. Space-based observatories that measure X-rays and ground-based instruments sensitive to very high-energy gamma rays have mapped emission from regions offset from the binary, along the jet axis. The spectra of these photons do not match what would be expected from hot gas alone. Instead, they resemble what we see when non-thermal processes are at work, involving particles that have been accelerated to energies far beyond those of the thermal background. One of the prime candidates for the mechanism behind this emission is inverse Compton scattering. In that process, electrons with very high energies pass through a field of lower energy photons starlight, infrared photons from dust, or the cosmic microwave background. Each time a fast electron collides with a photon, some of its kinetic energy can be transferred, boosting the photon to a much higher energy into the X-ray or gamma-ray regime. The electron loses a little energy in the exchange, and over many such interactions it gradually cools. A simple way to picture this is to imagine a stream of very fast balls moving through a cloud of slower, lighter ones. When a fast ball hits a slow one, it can send the slow ball off with a much higher speed than it had before, while the fast ball is slightly slowed. In the outer jets of SS-433, the electrons play the role of the fast balls, and the ambient photons are the slower ones. Near the base of the outer jets, where the electrons are freshly accelerated, we see the highest energy gamma rays. Farther along the jets, the photon energies tend to be lower, consistent with electrons that have lost energy through repeated scatterings and radiation. The question of how the electrons reach such high energies leads to the idea of diffusive shock acceleration. As the jets plow into the interstellar medium, they create shock fronts, regions where the flow slows abruptly and conditions change rapidly. Magnetic fields in and around these shocks can become tangled and turbulent. An electron moving in this environment may repeatedly cross the shock front, scattered back and forth by magnetic irregularities. Each crossing can add a small increment to its energy. Over many cycles, a fraction of electrons build up to very high energies before they eventually escape or radiate away their gains. An image from everyday experience might be the way a character in a game encounters repeated regions of enhanced speed on a track. Each time the character passes through one of these zones, its speed increases. If the track is arranged so that these zones can be crossed multiple times, the speed can build up significantly. In the jets of SS-433, the shock acts as that zone. The magnetic turbulence and the geometry of the flow keep some particles returning again and again, collecting energy until losses balance gains. The combination of inner and outer jets, X-ray and gamma-ray emission, and evidence for shock acceleration turns SS-433 into a kind of nearby workshop for understanding how jets operate. We can observe changes over human timescales, watch how the jets precess and how the emission regions respond, and test models that are then applied to much larger systems, such as quasars and the active cores of distant galaxies. The same basic processes, accretion onto compact objects, formation of jets, interaction with surrounding gas, and acceleration of particles to high energies, show up across a vast range of masses and distances. From the broad glow of quasar host galaxies to the narrow streams inside our own Milky Way, the patterns repeat with different scales and intensities. As surveys like Gaia and Vista map the stars of the galactic disk and bulge, instruments that watch jets and high-energy photons map the paths of energy leaving compact objects. Each perspective adds another layer to the hidden maps of our galaxy and of others, overlapping and extending, as if the sky were filled with interconnected diagrams drawn at different wavelengths and energies, all unfolding at their own unhurried pace. At first glance, it can seem puzzling that some of the largest black holes we know appear in a very young universe, as if they had reached extraordinary masses almost as soon as there was time to grow. When we look far enough away to see light that left its source billions of years ago, we find compact, brilliant cores in distant galaxies whose central black holes outweigh the one at the heart of the Milky Way by factors of thousands. The picture is striking, and it invites us to look more closely at what we are really seeing, and at how our way of observing shapes that impression. One of the most extreme examples discussed in this context is a quasar, known as TON 618. Its central black hole is estimated to have a mass of around 66 billion times that of the Sun, a mass comparable to the total mass in stars of a large galaxy. The accretion disk around it shines, with a power roughly equivalent to more than 100 trillion suns, so that the region close to the black hole outshines the entire host galaxy in which it resides. The light we see from TON 618 left when the universe was only a few billion years old, not long after galaxies first assembled into the structures we recognize today. To turn those numbers into a more tangible image, we can imagine a sphere around the black hole marking the region where its gravity traps light, the so-called event horizon. For TON 618, that sphere would be so large that a beam of light would need weeks to traverse its diameter. Yet the whole structure would still be tiny compared to the galaxy around it. What reaches our telescopes, however, is not light from the event horizon itself, but from the hot, glowing material in the accretion disk just outside, where gas falling inward is compressed and heated to very high temperatures. In that compact zone, gravitational energy is converted into radiation with remarkable efficiency, and the result is a quasar bright enough to be seen across a large fraction of the observable universe. When we set TON 618 beside the black hole at the center of our own galaxy, often called Sagittarius A*, the contrast is large. Sagittarius A times has a mass of about 4 million suns. The black hole in the center of the Andromeda galaxy is larger, a couple of 100 million solar masses, yet still far smaller than the giants we infer in some high redshift quasars. From this comparison, it is easy to form the impression that the very early universe was home to black holes far more massive than anything nearby, and that the largest ones somehow formed very quickly, almost in a rush. That impression softens when we consider how our observations are selected. At great distances, most sources are faint. For a telescope with a given sensitivity, only the brightest objects in a distant population rise above the detection threshold. This selection effect is often summarized under the name Malmquist bias. If we stand far outside a city at night, we do not see every window, We see the large illuminated signs, the stadium floodlights, the brightest towers. Many smaller lamps and modest buildings are present, but their light blends into the background. In a similar way, when we survey the distant universe, we tend to find the most luminous quasars powered by the most rapidly accreting black holes. The many galaxies whose central black holes are less active, or whose disks are not currently in a bright quasar phase, fall below the limit of our instruments. This means that our catalogue of high redshift quasars is not a complete inventory of black holes at that time. It is a list of those that happen to be shining most strongly in our direction. Closer to home in space and time, we know of large black holes in galaxies whose centers no longer blaze as quasars. Their accretion flows have quieted. Gas reaches them at a lower rate. Their light merges with the integrated glow of the surrounding stars. Some nearby elliptical galaxies, for example, host black holes with masses in the billions of solar masses. Yet they do not dominate the brightness of their hosts in the way that TON 618 does. They are present and massive, but they are no longer marked by extreme activity. Recognizing this selection effect helps to ease the apparent paradox. The fact that we observe luminous quasars like TON 618 inches, the early universe, does not mean that such giants exist only at early times. It tells us that, at large distances, those are the ones we can see most easily. Many similarly massive black holes at later times may not currently be in a state that produces quasar-level luminosity, and so they do not stand out as dramatically in our surveys. Our view is filtered by brightness, and what comes through that filter is the tip of a much larger population. A second piece of the picture comes from the conditions in the early universe itself. When the universe was only a few billion years old, gas in and between galaxies was more abundant, and had not yet been locked up in long-lived stars and compact remnants to the same extent as today. Young galaxies were still drawing in streams of gas along cosmic filaments, accumulating matter in their disks and central regions. Collisions and close passages between galaxies were more common, stirring up the gas and directing some of it toward the centers, where it could feed both rapid star formation and the growth of central black holes. We can think of this stage as a period when the building materials were still mostly in unassembled form. In a newly developing city, empty lots and open spaces can be filled quickly with tall structures if a large supply of raw material is available and if it can be delivered efficiently to a few key construction sites. Once the city is filled with many smaller buildings, it becomes harder to gather enough material in one place to erect something dramatically larger. The resources are distributed and locked into existing structures. In the same way, a gas-rich young universe makes it easier to drive large flows of matter into the central regions of galaxies, allowing black holes there to grow rapidly. Later on, when much of the gas has been converted into stars or heated and dispersed by previous episodes of activity, the supply becomes less straightforward. Over cosmic time, star formation and black hole growth both draw from the same reservoir of cold gas. Gas that goes into stars may later return to the interstellar medium through winds and stellar deaths, but a portion remains in compact remnants, white dwarfs, neutron stars, and small black holes. As these remnants accumulate, the fraction of baryonic matter that remains in a readily accretable gas phase declines, especially in the more massive galaxies where earlier activity has already transformed much of the raw material. The era when quasars are most common, often around a time when the universe was a few billion years old, coincides with an era of high cosmic star formation. Both phenomena are different expressions of this rich, gas-fed phase. As galaxies pass through these active periods, their shapes and stellar populations evolve. Gas-rich spiral galaxies, with prominent disks and visible dust lanes, can experience episodes of intense star formation, sometimes called starbursts, during which new stars are formed at a much higher rate than average. At the same time, energy from supernovae and from active galactic nuclei can heat and expel gas, driving winds that move material away from the central regions. Over time, repeated bursts and interactions can transform a disk galaxy into a smoother, more rounded system with less cold gas. In such elliptical galaxies, the star formation rate drops. Most of the stars are older and redder, and the overall appearance is more uniform. with little remaining dust. Nearby examples like the elliptical galaxy M105 show this kind of population. A smooth light profile dominated by old stars, with little evidence of recent star birth. The central black hole in such a galaxy may still be massive, but without a rich inflow of cold gas, it does not sustain a bright quasar phase. The galaxy has moved from a period of busy construction into a phase where the structures are largely in place and where changes occur over longer intervals. This slow shift from gas-rich, dusty spirals to gas-poor ellipticals is not a single path that every galaxy follows, but it is a common thread in many models of galaxy evolution. The most luminous quasars and the most intense starbursts often mark points along trajectories that lead toward more settled configurations. In that sense, the very large black holes we see at high redshift are not out of place. They are participants in a wider process in which galaxies and their central black holes grow together, draw down their gas supplies, and gradually change character. Closer to home, missions like Gaia and surveys like Vista give us detailed maps of the Milky Way's own disk and bulge, tracing old clusters and young stars, streams from cannibalized dwarf galaxies, and the remnants of gas flows that once fed our galaxy's central regions. By combining visible light astrometry with infrared imaging that pierces dust, we can read some of the fossil record of our own galaxy's active past, even though it no longer shines as a bright quasar. The structures we see today carry the imprint of earlier stages when the balance between gas, stars, and black hole accretion was different. As we look outward in space, and therefore backward in time, the luminous quasars act as distant markers of those earlier stages in other galaxies. As we look inward into the quieter centers of nearby systems, we find the outcomes: large black holes, old stellar populations, and morphologies that tell of gas that has been used and redistributed. The maps we build of these structures, across wavelengths and across epochs, form a connected picture in which early, bright activity and later, quieter forms are different phases of the same long evolution, continuing on scales of time that leave plenty of space for further change. When we look at the variety of galaxies that telescopes like Hubble have recorded, it is possible to feel as if we are watching a long, slow sequence of lives unfolding at different stages. Some disks look bright and structured, with clearly traced arms and a mix of colors. Others appear washed, their patterns fading. Some have no obvious disk at all, only a smooth glow with no sign of spiral structure. It is not a single, rigid path that every galaxy must follow. But taken together, these images hint at a loose cycle, and we can drift along it by moving from one example to the next. One of the calmer stages is represented by a galaxy like NGC 2336. In Hubble images, it appears as a large spiral with well-proportioned arms curling out from a central region, the pattern reminiscent of the Milky Way's own disk. The arms are populated by many bluish stars, the kind that burn hot and live briefly. Yet there are relatively few large red patches of ionized gas, the H2 regions that mark very intense star formation. Instead of a blaze of newborn clusters, we see smaller, scattered knots, as if the galaxy were forming stars steadily but not in a rush. The overall impression is of a system that has found a moderate rhythm, using its supply of gas in a way that can continue for a long time. We can picture such a galaxy as a city whose construction has settled into a sustainable pace. New neighborhoods appear along the spiral arms, but the skyline does not change dramatically from one era to the next. The gas and dust in the disk are dense enough to form new stars, but not so compressed that everything collapses at once into giant bursts. Density waves moving through the disk, like the patterns we discussed for the Milky Way's arms, shape where stars are born, but they do so without pushing the available material to extremes. This stage in a galaxy's life can last for billions of years, with the disk and arms remaining recognizable even as individual stars are born and age. In other systems, external influences or internal instabilities push the gas into more concentrated regions, and the rate of star formation rises sharply. Galaxies, such as NGC 972 or Messier 61, show this more intense phase. In images, their spiral arms are lined with bright red patches, where hydrogen glows in response to the radiation from newly formed massive stars. Around these pockets, clusters of hot, young stars shine in blue-white tones, making the arms look as though they have been traced with fresh strokes of light. The contrast between the central regions and the outer arms can sometimes reveal hints of tidal interactions, where neighboring galaxies in a cluster environment have tugged on the disk and disturbed its symmetry. M61, for example, shows fairly regular, symmetric arms near its center. But farther out, the pattern becomes less even, as if the outer disk had been nudged and stretched. In rich environments like the Virgo cluster, the gravity of nearby galaxies and of the cluster as a whole can compress gas in certain regions, prompting waves of star formation. In NGC 972, the large number of Hi2 regions suggests that the galaxy is experiencing a starburst, a period when it converts gas into stars much more rapidly than usual. These events do not last forever. They are more like brief, intense episodes when viewed on cosmic timescales, but they consume gas quickly and can leave lasting marks on the galaxy's structure. After such phases, or under the influence of the cluster environment, some spiral galaxies show signs that their supply of cold gas is being reduced. One example that often appears in this context is NGC 4921, sometimes described as an anemic spiral. The arms are still visible in structure, but their contrast is low. The bright red knots of star-forming regions are largely absent, and the overall color is paler. Dust lanes can still be traced, yet they do not stand out against a backdrop of vigorous star formation in the same way they do in galaxies like NGC 972. It is as if the familiar spiral pattern has been gently faded, leaving a memory of arms without the bright markers that once outlined them. In a cluster setting, interactions with the hot gas in the space between galaxies can strip material from the disk, especially gas in the outer regions. Over time, this process, together with the exhaustion of gas in the inner disk, can reduce the supply available for new stars. Without the ongoing birth of luminous, short-lived stars to highlight the arms, the spiral pattern gradually becomes less distinct. This is one route by which a galaxy can move toward a lenticular appearance, where a disk and central bulge remain, but without prominent arms. Lenticular galaxies, often classified between spirals and ellipticals in the Hubble sequence, include systems like NGC 2217, PGC 10922, and NGC 1947. In images, they show a bright central bulge and a flattened disk, sometimes with faint rings or subtle dust structures. But the grand, sweeping spiral arms are gone or barely traced. The light is dominated by older, more evenly distributed stars, giving the whole system a smooth, almost polished look. In some, a bar can still be seen crossing the central region, hinting at internal processes that once helped to drive gas inward. In others, the disk is relatively featureless, more like a lens of starlight than a swirling pattern. These lenticular systems can be thought of as transition states, places where the disk structure persists, but the conditions needed to sustain clear spiral arms are no longer present. The density waves that once organized the gas and young stars into visible arms still exist in some form, but with less gas to work on, their imprint on the light distribution is weaker. The supply of cold gas has been thinned by past star formation, by outflows driven from the central regions, or by interactions with the galaxy's surroundings. What remains continues to orbit in a flattened configuration, but the visual cues that once distinguished arms fade into a more uniform brightness. Further along this informal sequence, we encounter galaxies like M105, a nearby elliptical system. In Hubble's view, M105 appears as a smooth, luminous ellipse of stars with no obvious disk, no arms, and little or no visible dust. When we zoom in, the field resolves into countless individual stars, predominantly older and cooler, giving the galaxy a warm, reddish tone. The rate of ongoing star formation in a system like this is extremely low, Estimates for M105 suggest something like one sun-like star, forming only over intervals far longer than a human lifetime, stretched out by orders of magnitude. The galaxy's light is the accumulated glow of stars born long ago, slowly evolving internally, without large-scale changes in structure. We can imagine such an elliptical galaxy as a city that has completed its major phases of construction. New buildings still appear here and there, but the skyline is set, and most of the activity takes place within existing structures. Any remaining gas is thinly spread, often heated by past events or by the cumulative energy of old stars and central activity, making it less likely to condense into new star-forming clouds. Many elliptical galaxies host massive black holes in their centers, but without large inflows of cold gas, these black holes accrete slowly, and any active phases are relatively modest compared to the bright quasar episodes of the past. It is important to remember that these stages spiral with moderate star formation. Starburst galaxy, anemic spiral, lenticular, and elliptical do not form a strict ladder that every galaxy must climb in the same way. Some galaxies may remain in a spiral state for most of their lives. Others may be transformed by mergers into ellipticals more quickly. Dwarf galaxies can follow different paths. Yet when we arrange examples like NGC 2336, NGC 972, M61, NGC 4921, lenticular systems, and M105 side by side, a broad pattern emerges. The availability and distribution of gas, the history of interactions and mergers, and the influence of environment all guide galaxies along courses that often move from gas-rich, structured disks towards smoother, gas-poor forms. Across this variety, the same physical ingredients recur: gravity shaping orbits, gas cooling and collapsing into stars, feedback from stars and black holes stirring and heating the medium, and the slow influence of surrounding structures. Missions such as Gaia, mapping the motions of stars in the Milky Way, and infrared surveys from telescopes like Vista, tracing hidden star-forming regions, provide detailed views of one galaxy within this larger family. Hubble's images of other galaxies, spread across different distances and environments, place our home within a broader context, showing many possible expressions of similar processes. As we let these images and maps overlap in our thoughts, the life of a galaxy becomes less a fixed path and more a collection of possible routes through time, each one marked by the way gas, stars, and dark matter interact. The disks and bulges, arms and clusters, lenticular lenses and smooth ellipses all contribute to a quiet sense of continuity as structures shift slowly across epochs far longer than any single observation can follow directly, yet still leave their traces in the shapes we see now. There are places in the universe where many familiar processes seem to be turned up a little higher, as if nature had chosen to show us certain patterns in a concentrated form. Some of these places are entire small galaxies that burn through their gas more quickly than most. Others are compact regions inside our own Milky Way, where stars crowd together in densities far above what we experience near the Sunday. On still larger scales, there are clusters of galaxies whose combined gravity bends the paths of light, transforming them into large, natural lenses. Each of these settings becomes a kind of laboratory, a place where ideas about galaxy evolution, star formation, and gravity can be tested in sharper relief. NGC 4449 is one of those laboratories. It is a dwarf galaxy, only a few tens of thousands of light-years across, compared with the Milky Way's roughly 100,000 light-year span. In deep images, it does not show the tidy spiral arms of a classic disk. Instead, it appears like a luminous cloud of stars and gas, with a somewhat irregular outline. Across this cloud, bright knots of blue and red light are scattered. Blue clusters of young stars and reddish regions of ionized hydrogen where gas glows in response to the radiation of massive newborn stars. These features indicate that NGC 4449 is in the midst of a starburst, a phase when it forms stars at a much higher rate than a typical galaxy of its size. Along one side of NGC 4449, astronomers have found a faint, elongated stream of older, redder stars that extends outward like a tail. This structure is interpreted as the remains of an even smaller companion galaxy that has been stretched by tidal forces. Its stars pulled into a long arc as it interacted with NGC 4449. The combination of a central starburst and an extended stellar stream suggests that NGC 4449 is not evolving in isolation. Its group environment and past interactions have compressed gas in some regions, triggering new star formation, while at the same time reshaping its overall structure. In this way, a dwarf galaxy, like NGC 4449, shows many of the same processes we see in larger systems: bursts of star formation, the influence of neighbors, and the gradual incorporation of smaller galaxies into larger ones. What happens on a smaller canvas is still part of the broader pattern in which galaxies grow by merging and by drawing in gas. Dwarf starbursts may eventually be folded into bigger galaxies, contributing their stars and gas, and leaving behind faint streams similar to those that Gaia has revealed in the halo of the Milky Way, where the three-dimensional motions of stars trace the remnants of long-ago mergers. From this small, active galaxy, we can let our attention drift back into our own. Within the Milky Way's Carina arm lies a large, bright nebula known as NGC 3603, and embedded in it is a very dense star cluster called HD 97950. When we look at this region with instruments like Hubble, we see a crowded swarm of brilliant stars packed into a compact volume, surrounded by sculpted clouds of gas. The densities here are far higher than in the solar neighborhood. Massive stars, some of them in the class known as Wolf-Rayet stars, with initial masses approaching 100 times that of the Sun, dominate the light. Their radiation and stellar winds carve cavities in the surrounding gas, pushing material aside and piling it up into ridges and filaments that outline the boundaries of the cluster's influence. HD 97950 is sometimes described as a superstar cluster, and it offers a local example of the kind of intense, star-forming regions we infer in distant starburst galaxies. Many massive stars are forming in a relatively small volume and over a relatively short time interval. In the future, some of these stars will end their lives in energetic events, enriching the surrounding gas with heavier elements. The combined effect of their winds, radiation, and eventual deaths stirs and heats the interstellar medium, influencing how future generations of stars will form in the nearby disk. Surveys like Gaia's and Vista's contribute to our understanding of such regions in complementary ways. Gaia, with its precise measurements of positions and proper motions for about 2 billion stars, can follow the motions of stars in clusters, showing how they drift apart over time and how they move within the Milky Way's gravitational field. Vista, observing in infrared, can look through much of the dust that surrounds young clusters, revealing stars that are still partly embedded in their birth clouds, particularly in the bulge and inner disk. Together, these maps help to place extreme regions like NGC 3603 within the broader structure of the galaxy, connecting local starburst activity to the larger patterns of gas flow and cluster formation that shape the Milky Way's disk and bulge. If NGC 4449 and HD 97950 show us star formation and interaction on small and intermediate scales, galaxy clusters such as Abell 2218 and Abell 1703 reveal something different: the way that large concentrations of mass affect the paths of light itself. These clusters are located billions of light years away and contain hundreds of galaxies bound together by their mutual gravity, as well as hot gas and a substantial component of dark matter. The combined mass of all these components curves space-time enough that light from more distant galaxies, passing behind the cluster on its way to us, is deflected. In images, the result is a pattern of distorted arcs and stretched shapes around the central region of the cluster. Background galaxies that would otherwise be too faint and small for us to detect are magnified and elongated into thin, curved features. It is reminiscent of looking through a thick, uneven glass lens that bends and magnifies parts of the scene behind it. In Able 2218, for example, observations have revealed the same distant galaxy appearing in more than one place in the field, as separate arcs produced by different light paths around the cluster's mass. The light from this background galaxy has traveled for roughly 13 billion years, carrying information from an era not long after galaxies began to form. These gravitational lenses serve two roles. First, they allow us to see very distant galaxies that would otherwise fall below our detection thresholds. The magnification can bring into view structures that would be invisible without the lensing effect, giving us a glimpse of galaxies at stages of their evolution that are otherwise hard to study directly. Second, by analyzing the shapes and positions of the arcs, astronomers can reconstruct the distribution of mass in the lensing cluster. The amount and pattern of distortion depend not only on the visible galaxies and gas, but also on the dark matter that does not emit light. In that way, the cluster becomes a map of dark matter's influence, traced by the way it bends light from the background. We can think of these clusters as large-scale counterparts to the smaller lenses we sometimes infer inside our own galaxy, where compact objects briefly magnify background stars as they pass in front of them. On a grander scale, Abell 2218 and Abell 1703 turn entire regions of the sky into fields of magnified distant images, extending our reach into earlier cosmic times. At the same time, the clusters themselves are part of the larger story of structure formation, assembled from the merging of smaller groups and galaxies, and offering another perspective on how matter arranges itself under gravity. Taken together, a dwarf starburst like NGC 4449, a superstar cluster like HD 97950 inches, NGC 3603, and lensing clusters such as Abell 2218 and Abell 1703 form a trio of special settings in which key processes can be examined in sharper focus. In each case, the same underlying ingredients appear: gas cooling and collapsing into stars, galaxies interacting and exchanging material, and mass both visible and dark shaping the motions of stars and the paths of photons. As Gaia continues to refine its three-dimensional map of the Milky Way's 2 billion stars, revealing streams from past mergers and the structure of the disk and halo, and as VISTA's infrared survey fills in more than 1 billion previously hidden sources in the bulge and plane, these local and distant laboratories become easier to place within a wider network. The visible light surveys show where stars are and how they move. The infrared maps show where dust once obscured whole populations. The lenses extend our view to galaxies whose light set out toward us when the universe was very young. The result is an expanding set of overlapping maps, drawn at different scales and wavelengths, through which we can follow the quiet transformations of galaxies and clusters as they continue along their slow paths through space and time. Some galaxies look as though we have caught them in the middle of a sentence rather than at the end of one. Their shapes stretched, twisted, or ringed with light, as if a quiet story of interaction were being told frame by frame. Among these are systems in which the dense core of a galaxy seems to stand almost alone, or where ripples of star formation form bright circles, or where several galaxies move together along invisible strands of the cosmic web. When we move our attention through these scenes, we begin to sense how the future of our own Milky Way may be written into them in ways that are subtle rather than dramatic. In the Virgo region of the sky, a large elliptical galaxy called M60 shares the field with a smaller spiral neighbor, NGC 4647. In detailed images, M60 appears as a smooth, luminous ellipse with no obvious spiral structure. Its light dominated by old stars, and its central region hosting a black hole with a mass of several billion suns. NGC 4647, nearby in projection, shows the familiar disk and spiral arms. But the two do not yet display the strongly distorted shapes that would point to a close, disruptive encounter. They are part of the same environment, part of the same cluster, yet in the snapshot we see, each still largely keeps its own outline. Not far from this pair, though, another object stands out. a tiny galaxy called M60 UCD1. It is only a few hundred light-years across, far smaller than a normal galaxy. But inside that small volume, it carries the mass of hundreds of millions of suns. The density of stars is thousands of times higher than in the region around the Sunday. If we imagine standing on a hypothetical planet in such a place, the sky would be crowded with bright stars in every direction, with very little dark space between them. At the center of M60 UCD1, there is evidence for a black hole of around 10 million solar masses, a mass surprisingly large compared with the number of stars that now surround it. One way to interpret such an object is as the exposed core of a once larger galaxy. Over many passages through the cluster, tidal forces from giants like M60 can strip away the outer layers of a smaller galaxy, removing its extended disk and halo and leaving behind a compact, star-rich nucleus. The central black hole remains, now residing in a much smaller stellar system than the one that originally grew around it. In this view, ultra-compact dwarfs like M60 UCD1 are fossil records of past interactions. Their high densities and relatively oversized central black holes telling us how matter can be rearranged by repeated encounters in crowded environments. From this dense remnant and its large neighbor, we can let our attention drift to systems where the signatures of interaction are written not as compact cores but as wide, bright rings and arcs. ARP 147 is one such pair. One member is a more or less smooth, compact object, while the other forms a striking ring of hot, blue stars surrounding a darker interior, with a redder knot offset to one side. The configuration suggests that a compact galaxy has passed through the disk of its partner, sending a wave of compression outward through the gas. As the wave travels, it triggers star formation along a circular front, much as a disturbance on a pond sends ripples outward that catch the light. The ring we see is not a rigid structure, but a moving zone, where gas has recently been compressed enough to form stars. In another scene, the galaxy NGC 1097 presents a bright central region encircled by a ring of star-forming activity. The ring has the appearance of a glowing loop around the core, sometimes likened to the iris around a pupil. Beyond it, faint, linear features extend into space in a rough X shape, like delicate streams branching away from the main body. These streams are thought to be the remains of smaller galaxies that have been drawn into NGC 1097 inches the past, their stars stretched into long filaments by gravity. The bright ring near the center, meanwhile, marks a zone where gas has accumulated and is forming stars at an elevated rate, possibly guided there by a bar structure in the inner disk. Together, systems like ARP 147 and NGC 1097 illustrate how encounters can both reshape existing structures and stimulate new star formation. Passing galaxies can launch waves that reorganize gas into rings, while repeated minor mergers can leave behind arcs and plumes that slowly fade but still outline previous paths. The galaxies are not shattered, they are reconfigured, their stars continuing to orbit in new patterns, while gas clouds are compressed in some regions and thinned in others. Other examples highlight the way smaller galaxies are especially responsive to such influences. ARP 142, sometimes nicknamed the Penguin and the Egg, pairs a fairly regular elliptical galaxy with a distorted spiral whose disk has been pulled into a curved, asymmetric shape. One part of the spiral arcs upward, giving the impression of a figure leaning over a compact, round companion. Along the stretched section of the disk, bright knots of star formation cluster, tracing where tidal forces have concentrated gas. The elliptical galaxy appears comparatively undisturbed, while the spiral carries most of the visible imprint of the interaction. In the dwarf galaxy NGC 1569, the entire body looks like a single, glowing, star-forming complex. It is small, but almost every part of it is dominated by ionized gas regions and clusters of young stars. The rate of star formation, when scaled to its size, is far higher than in the Milky Way. Nearby groups, such as the Maffei group, contribute gravitational influences that can perturb NGC 1569's gas, compressing it and triggering a starburst. The combined winds and radiation from the young, massive stars push on the surrounding medium, driving gas outward and reshaping the galaxy's interstellar environment. In these cases, the smaller partner often shows the clearest deformation and the most intense bursts of star formation. The gravitational field of a larger neighbor can pull on the smaller galaxy's structure, drawing out streams and tails and concentrating gas in certain regions. Over time, repeated interactions and the loss of gas can change the smaller galaxy's path through the cycle described earlier, pushing it more rapidly toward a state where star formation slows and its shape becomes simpler. On even larger scales, systems like ARP 272 remind us that these interactions occur within a much broader context. ARP 272 is a group of at least 3 galaxies whose spiral arms appear drawn out and intertwined, with bridges and streams linking one to another. They reside in the Hercules supercluster region, itself part of a vast network of galaxy clusters and filaments that span the observable universe. When we model the distribution of matter on these scales, we see a pattern, sometimes called the cosmic web. Dense filaments, where galaxies and clusters concentrate, and wide voids between them, where very few galaxies are found. We can picture this as a 3-dimensional network, with knots at the intersections where superclusters gather and strands connecting them. Along the strands, galaxies move under gravity, sometimes falling toward cluster centers, sometimes orbiting within groups. Where the density of galaxies is high, close passages and mergers are more likely, though they still unfold over hundreds of millions or billions of years. In more isolated regions, a galaxy may evolve with fewer strong encounters. But even there, the overall expansion of the universe and small-scale interactions gently reshape its surroundings. Our own Milky Way lives within this network, in a smaller group of galaxies that in turn is a part of the Virgo supercluster region. Gaia's precise 3-dimensional map of around 2 billion stars has begun to show how our galaxy has grown by absorbing dwarf companions, leaving behind streams and globular clusters that trace their former paths. VISTA's long-term infrared survey adds the largest and most detailed map of the inner Milky Way, revealing over 1 billion previously hidden objects and young stars in the bulge, so that we can follow both the ancient populations in the halo and bulge and the ongoing star formation in the disk. Together, these maps place the Milky Way within the wider story of galaxies that drift along filaments, interact, and gradually change shape. Far in the future, on timescales of several billion years, the Milky Way and the Andromeda Galaxy are expected to move closer and eventually blend into a single, larger system in an event that will resemble some of the interacting pairs we see today. The stars themselves will mostly pass at great distances from each other, with orbits being rearranged rather than brought to abrupt ends. Gas clouds will shift, concentrate, and form new generations of stars, while the central black holes spiral slowly toward one another deep inside the merged galaxy's core. When we look at unusual systems like M60 UCD1, ring galaxies like ARP 147, distorted pairs like ARP 142, and intertwined groups like ARP 272, we are seeing different moments in this long cycle as it plays out in various environments. The detailed maps from Gaia, VISTA, and many other instruments give us increasingly fine views of one part of that cycle within our own galaxy. The distant images from Hubble and other telescopes extend our view outward, showing many other instances along similar paths. All of these scenes together form a set of overlapping guides to how galaxies move, merge, and slowly transform, while the larger structure of the cosmic web holds them in its quiet framework. Across the history of astronomy, our maps of galaxies have often been drawn with a kind of quiet confidence that the sky did not fully justify. Each generation has taken the brightest features it could see, connected them into patterns, and called that a picture of reality. Only later, with new instruments and new wavelengths, have we discovered how much was missing at the edges and in the dimmer parts of the frame, and how many of our neat diagrams were only first drafts. One of the most persistent influences on those drafts has been brightness itself. Telescopes, photographic plates, and digital surveys all have limits. Past a certain faintness, objects simply do not register. At great distances, this effect becomes more pronounced. When we look far out into space, we are most likely to detect galaxies that are large, rich in stars, and actively forming new ones. Quasars, with their compact, brilliant cores, easily stand out, while more modest galaxies at the same distance blend into the background. Astronomers describe this tendency as a brightness bias, sometimes under the label of Malmquist bias. And it shapes not only which quasars and galaxies we record, but also which stars inside our own Milky Way end up in catalogs. The result is that, for a long time, our maps of the universe were stacked with the most luminous members of each population. We had plenty of spirals with clear arms, bright ellipticals in clusters, prominent quasars, and the bluest, most powerful stars. What we lacked were the low-surface brightness galaxies that spread their light thinly over wide areas and the diffuse outskirts of larger systems. Only with deeper and wider digital surveys did very faint, ultra-diffuse galaxies begin to appear, adding ghostly structures to clusters where previously we saw only the brightest members. The faint end of the star counts in the Milky Way has also filled in, as telescopes like Gaia patiently accumulate enough measurements to bring even dim, red stars into the three-dimensional map. Another layer of distortion comes from dust. Invisible light. The Milky Way's plane is riddled with dark patches and streaks where interstellar dust absorbs and scatters starlight. Around the galactic center, this effect becomes so strong that the region was once labeled a zone of avoidance, a band where distant galaxies were hard to find, and where the internal structure of our own galaxy was difficult to trace. Early diagrams of the Milky Way showed arms and a bulge inferred from incomplete counts, with large uncertainties about the true shape of the central regions. The dust acted like a mask. What we saw in visible light was a version of the disk and bulge with pieces missing. Infrared observations began to loosen this mask. Instruments on board satellites and on the ground could record light at wavelengths where dust is more transparent. VISTA, the telescope in Chile dedicated to wide-field infrared surveys, has played a central role here. Over more than a decade, its VVV and VVVX surveys have produced the largest and most detailed infrared map of the Milky Way to date, revealing more than 1 billion previously hidden sources and entire populations of young stars in the bulge. Cepheid variables and RR Lyrae stars that lie behind the dust, along with new globular clusters and open clusters near the plane, have been brought into view, allowing astronomers to refine the structure of the inner disk and bar, and to revise our picture of how the central regions have grown over time. At the same time, Gaia, orbiting near the L2 point, with its 2 telescopes and vast focal plane, has built a precise three-dimensional map of about 2 billion stars over roughly a decade of observations. By measuring parallax and proper motion with high accuracy, Gaia reveals streams of stars left behind by cannibalized dwarf galaxies and clarifies the rotation of the disk and the behavior of the halo. When Gaia's distances and motions are combined with VISTA's ability to see through dust, the map of the Milky Way's disk and bulge becomes far more complete, tying together the ancient heart, traced by old clusters, with regions where new star formation continues. Dust and brightness are not the only ways that our impressions can be skewed. The appearance of a galaxy changes markedly with wavelength. On early blue-sensitive photographic plates, spiral galaxies often look strongly structured, their arms marked by bright, young stars and H2 regions. Viewed in the ultraviolet, those same galaxies seem even more clumpy and filamentary because we are highlighting the very youngest stellar populations. In infrared images, the emphasis shifts to older, cooler stars and warm dust, and the overall structure may appear smoother, with the bulge and bar more clearly defined. At radio wavelengths, extended disks of neutral hydrogen and the presence of jets become visible, adding yet another aspect. For a period, some galaxies were labeled peculiar or irregular, chiefly because we had seen only one of these faces. A system that looks chaotic in ultraviolet might align neatly with familiar patterns when seen in infrared, where the underlying stellar mass distribution is clearer. multi-wavelength observations have gradually shown that many of the oddities belong naturally on an evolutionary sequence, where gas is consumed, stars age and fade, and interactions reshape disks and halos. What once looked like exceptions to the rule often turn out to be snapshots of common processes caught at particular stages. On larger scales, gravity itself can create illusions. When light from a distant galaxy passes near a massive cluster such as Abell 2218 or Abell 1703, space-time curvature bends the path of the light. To our telescopes, the background galaxy's image can appear stretched into an arc, multiplied into several images, or arranged into partial rings. Early observations of such arcs raised questions about whether they represented very unusual ring-shaped galaxies. The development of gravitational lensing theory and comparisons between cluster masses and arc shapes made it clear that we were seeing ordinary background galaxies whose images had been distorted by the intervening mass. Understanding gravitational lensing allowed astronomers not only to correct those misinterpretations, but also to turn the effect into a tool. By mapping the positions and shapes of many lensed images in a cluster, it becomes possible to reconstruct the distribution of total mass, including dark matter that does not emit light, but still curves spacetime. This lensing-based mass map can then be compared with the locations of visible galaxies and hot gas, revealing how matter is arranged in the cluster and along the filaments of the cosmic web. The same phenomenon, applied statistically to slight distortions in large samples of background galaxies, has become a way to study the distribution of dark matter on cosmological scales. Beyond observational biases, our theoretical frameworks also influence how we draw maps. In some cases, equations and models point toward entities that cannot yet be observed directly. The positions of Neptune and Uranus were refined using theoretical predictions before direct imaging resolved their detailed features. In galactic astronomy, the flat rotation curves of spiral galaxies suggested the presence of additional mass beyond what could be accounted for by stars and gas alone. This led to the idea of dark matter halos surrounding galaxies, structures that now appear in most large-scale simulations and that influence how we interpret lensing and motion data. On even larger scales, the observed acceleration of cosmic expansion led to the introduction of dark energy into our models, a component that affects how distances and redshifts relate. These elements, dark matter, dark energy, are now woven into cosmological maps, yet they remain inferred rather than directly imaged. Discrepancies between different measurements of the expansion rate, such as tensions between local distance ladder results and early universe inferences, are reminders that our models, while powerful, are still approximations. The remaining differences may point toward subtle systematic errors or toward additional physics we have not yet fully described. When we look back over this chain of revisions, it is not a story of constant failure. Each generation of maps captured something true within the limits of the data available at the time. Star charts that treated the Milky Way as the entire universe were not wrong about the distribution of visible stars on the sky. They were incomplete about what lay beyond. Early sketches of the Milky Way's spiral arms were not fabrications. They were partial outlines drawn through the gaps left by dust and brightness limits. As Gaia and Vista add their layers, 2 billion stars with measured motions, more than 1 billion hidden objects revealed in infrared, the older maps are not discarded but nested within a larger frame. By combining visible light astrometry and infrared imaging, astronomers now trace both the ancient heart of the galaxy, with its old bulge and globular clusters near the center, and its ongoing star formation in the disk and inner regions. Similar combinations across wavelengths and surveys extend outward to galaxies of all types and environments. The picture is still being adjusted, and many of the biases and uncertainties we live with now will likely seem simple to astronomers working with richer data in the future, in the same way that our current understanding makes earlier misconceptions feel distant and almost endearing. The process continues, with new instruments preparing to widen and deepen our maps once again. In the present era, even as we become aware of how often our maps have shifted, New observatories and simulations are being designed specifically to follow the faint structures and subtle distortions that older instruments could not reach. Rather than a single definitive chart, the future of galactic cartography looks more like an evolving atlas in which space, time, and invisible matter are all recorded together, updated as new data arrive. One of the missions that will play a central role in this is Euclid, a space telescope developed by the European Space Agency with contributions from NASA. Euclid is designed to survey a large portion of the sky, mapping billions of galaxies out to distances where their light has been traveling for around 10 billion years. Its main goal is to study the distribution of matter in the universe and to probe the history of cosmic expansion. To do this, Euclid will use weak gravitational lensing. The tiny, coherent distortions in the shapes of background galaxies caused by the cumulative mass along the line of sight, where clusters like Abell 2218 produce dramatic arcs. Weak lensing creates only slight stretches and shears in galaxy images, barely noticeable for any single object. By measuring these distortions statistically across large numbers of galaxies, Euclid can reconstruct how dark matter is distributed on large scales, mapping filaments and knots in 3 dimensions. At the same time, by combining redshift information with the angular distribution of galaxies, it can chart how structures have grown over time, providing another way to study dark energy and the geometry of the universe. In essence, Euclid will extend the idea of gravitational lensing from a handful of striking examples to a vast, systematic atlas of the cosmic web. While Euclid focuses on the large-scale structure, the Vera C. Rubin Observatory in Chile will transform our view of the changing sky. Its wide-field telescope and 3.2 gigapixel camera are designed to repeatedly image the same areas of the southern sky over a period of about 10 years. This survey, often referred to as the Legacy Survey of Space and Time, will record billions of galaxies and stars in multiple filters, building up deep co-added images while also capturing how objects vary over time. For our maps, this adds 2 key dimensions. First, the deep stacked images will reveal extremely faint structures, ultra-diffuse galaxies, low surface brightness, tidal streams around nearby galaxies, and the extended halos of clusters. These are precisely the parts of the brightness spectrum that earlier surveys struggled to include. Second, the time domain data will show variable stars, transient events, and slow structural changes in a way that allows patterns of motion and variability to be mapped alongside positions. Weak lensing measurements from Rubin will complement those from Euclid, while the discovery of countless variable sources will enrich distance ladders and improve our understanding of how galaxies change on humanly accessible timescales. Another forthcoming observatory, the Nancy Grace Roman Space Telescope, will bring wide-field infrared imaging to space in a way that bridges local and cosmological scales. Roman's instruments will survey the plane and bulge of the Milky Way in infrared, mapping tens of billions of stars and the dust between them. This will extend the kind of work VISTA has done from the ground, offering sharper resolution and a stable space-based platform. The resulting maps will refine our knowledge of the Milky Way's spiral arms, central bar, and the distribution of gas and dust in the disk and bulge, tying directly back to the themes of our earlier chapters. At the same time, Roman will conduct cosmological surveys that probe distant galaxies, supernovae, and large-scale structure. By observing galaxies and clusters in infrared, it will complement Euclid's optical view, help to trace structures in regions where dust obscuration is significant, and study cosmic voids, the large, relatively empty regions between filaments. Measurements of distances and redshifts from Roman's data will feed into constraints on dark energy and further refine our picture of how the expansion of the universe has changed over time. Parallel to these observational efforts, large computer simulations are creating virtual universes that can be compared directly with surveys. Projects like Illustris TNG, and Eagle start from initial conditions that reflect the early universe, then evolve forward using equations that describe gravity, dark matter, gas dynamics, star formation, and feedback from stars and black holes. Over billions of simulated years, filaments emerge, Galaxies form at the intersections, and mergers and interactions drive changes in morphology, much as we see in real observations. These simulations generate synthetic sky maps, mock images and catalogs of galaxies that can be observed in different wavelengths and from different viewpoints. By comparing them with data from Gaia, Vista, Hubble, Euclid, Rubin, Roman, and other surveys, astronomers can test whether the assumed physics in the simulations reproduces the distribution and properties of galaxies we actually see. If a simulation produces too many massive ellipticals, too few dwarf galaxies, or the wrong pattern of dark matter clustering, it suggests that some aspect of the model needs adjustment. In this sense, the virtual universes serve as draft maps that can be aligned with the real sky, with discrepancies pointing toward missing ingredients in our understanding. As these observational and simulated maps grow richer, the process of revising our picture of galaxies becomes more continuous. Instead of waiting for single dramatic discoveries to overturn old paradigms, we see a gradual flow of adjustments. New star clusters added to the Milky Way's inventory, faint streams traced around nearby galaxies, weak lensing patterns, sharpening the outlines of dark matter filaments, discrepancies between simulations and observations, prompting refinements in feedback models or dark matter properties. The atlas of galaxies becomes something that is updated in near real time, with layers of data accumulating over years and decades. From our current vantage point, it is clear that many of the ideas we treat as solid will eventually be revisited. Future astronomers, working with even more comprehensive surveys and more powerful simulations, will likely look back at our assumptions about dark energy, galaxy evolution, or the exact structure of the Milky Way, in much the same way we now view early drawings that placed our galaxy at the center of the cosmos. Those earlier maps were not pointless, they were stepping stones. We can think of ourselves as living in the midst of an ongoing project to chart a universe that still keeps much of its matter and energy in forms we cannot see directly. Gaia's precise stellar motions, Vista's infrared view of the dusty bulge, the upcoming measurements from Euclid, Rubin, and Roman, and the expanding libraries of virtual galaxies all fold into that project. As time goes on, the outlines on our maps will continue to shift, not in sudden jumps, but in a steady accumulation of detail, while galaxies and clusters move along their paths through the larger network of filaments and voids, carrying on their own histories at a pace that quietly exceeds any single map we can draw. Through this journey, we have seen that understanding galaxies has never been a simple task. What humanity once held with confidence often reflected only the limits of our instruments, of light itself, and of the vantage point available to us at any given moment. From maps obscured by cosmic dust, to biases shaped by brightness, to structures that reveal themselves only when observed at different wavelengths, the universe has patiently taught us humility. Galaxies do not stand still waiting to be understood. They move, they transform, and they carry within them the memory of collisions, mergers, and renewal unfolding over billions of years. Thank you for taking the time to listen and to accompany us on this unhurried journey. Each moment of your attention becomes part of a shared contemplative path, where science and silence meet. In the episodes to come, we will continue to uncover new surprises together, reaching toward deeper secrets of the vast and expansive universe, where every answer gently gives rise to another question.